My name is Shirley and I will be presenting the introduction to our HT3 experiment on the performance of a double tube heat exchanger. The objective of this experiment are to investigate the effect of cold water flow rate on heat transfer efficiency, the real heat transfer coefficient, and the theoretical heat transfer coefficient. In addition, we aim to determine the best operating condition by comparing co-current and counter-current configuration, as well as laminar and turbulent flow regime. Moving on to the background material, a double tube heat exchanger transfers heat between two fluids without direct mixing. Heat transfer occurs through convection between the fluid and the tube wall, and conduction through tube wall. The heat transfer rate depends on the flow rate and temperature difference, while the Reynolds number is used to determine the flow regime. Generally, higher flow rate enhance heat transfer, and counter-current flow provide better thermal performance than co-current flow. This experiment was conducted using the KC23401 double tube heat exchanger unit, which consists of heat tank, circulation pump, flow meter, temperature sensor, and control valve. The equipment allows us to control flow rate and monitor temperature changes under different operating conditions. Heat exchangers are widely used in industries such as chemical processing, power generation, food manufacturing, and refrigeration systems. Understanding their performance is important for improving energy efficiency and reducing operating costs. Therefore, this experiment provides valuable insight into the factors that influence heat exchanger performance and their industrial application. That concludes the introduction section. Thank you.
Hello, my name is Mary Joyce Christie. So today I'll be talking about the methodology. The material used in this experiment are double heat exchanger bed 010, heating tank, control valve, flow meter, and circulation pumps. Next, we're moving on to the procedure of this experiment. The first step is to ensure all valves are closed before starting the experiment. The second is to set the hot water temperature to 50 degrees Celsius and the flow rate to constant. The next step is to choose the arrangement to co-current or counter-current flow. The next one is to adjust the cold water flow rate to predetermined value. Next step is to monitor the temperature reading and wait until constant for 2 minutes. The next one is to record the temperature in the data table. The next step will be on the next slide. Continuing from the previous slide, the next step is to repeat step 4 until 6 for various cold water flow rate. The next one is to change the flow to the opposite configuration. The next one is to compare the efficiency, the real heat transfer coefficient KRE, and the theoretical heat transfer coefficient KTH. Last but not least is to investigate the best condition of heat exchanger in the double heat exchanger.
Hello and greetings. My name is Muhammad Nur Askandar bin James. Now I will be presenting about the result of our experiment for part A, co-current. So, as you can see from the data, we take each temperature from each flow rate from 10 liter per minute to 50 liter per minute. For T hot in and T hot out, we also take the differences, negative 8.7, which is getting higher from 10 to 50 liter per minute, start from negative 8.7 to negative 15.9 degrees Celsius. Same goes to the temperature of cold in and cold out. We also take finding the differences, which is getting smaller from 32.5 to 7.9. Next, from the all experimental data and the information of our heat exchanger, we taken the numbers and make a calculation to find the LMTD, KRE, and efficiency of each flow rates. As you can see in LMTD, from 28.6 getting higher to get 38 and 6.6 degrees Celsius. As for KRE, we show a different kind of pattern in KRE, which is 39,600, 32,400, 41,200, 45,100, and 35,700 from 10 L per minute to 50 liter per minute. As for the efficiency, it's getting smaller from 0.64 to 0.16. That's all.
Assalamualaikum and good day everyone. My name is Maizra Mazani and I will be presenting the results for Part B counter-current flow configuration. In this experiment, we kept the hot fluid flow rate constant at 600 cm3 per minute while varying the cold water flow rate to evaluate the thermal performance of the counter-current heat exchanger. Now, let's look at the key findings. First, the heat transfer rate, Q. As the cold water flow rate increases from 10 to 40 liters per minute, Q rises significantly from about 25 kilowatts to over 34 kilowatts. This is due to enhanced turbulence and a higher convection coefficient. However, at 50 liters per minute, we observe a slight drop in Q. This suggests that despite better mixing, the residence time becomes too short for effective heat exchange. Next, the log mean temperature difference, or LMTD. It increases steadily with flow rate ranging from roughly 19.5 degrees Celsius to nearly 35 degrees Celsius. More importantly, the overall heat transfer coefficient, U, in this counter-current setup is significantly higher than in co-current flow, which confirms that this configuration is thermally superior. And finally, let's discuss efficiency. Interestingly, at low flow rates, specifically 10 liters per minute, our calculated efficiency exceeded 1.0, reaching 2.69. This isn't an error. It occurs because the cold fluid's heat capacity limits the maximum possible heat transfer, allowing our highly effective countercurrent exchanger to surpass the conventional baseline. As flow rate increases, efficiency decreases as we approach the system practical limits. And to wrap up, the countercurrent configuration demonstrates excellent thermal performance, though designers must balance higher flow rates against reduced contact time. That's all from me, thank you.
To conclude, the objective of this experiment was successfully met, demonstrating that the heat transfer characteristics of the system are highly dependent on flow configuration and velocity. Based on our result, we can draw two conclusions. First, regarding the system configuration, countercurrent flow is thermally superior to the cold current setup, yielding significantly higher overall heat transfer coefficient. Second, regarding the flow rate, heat transfer consistently peaked at 40 liters per minute due to maximized turbulence. However, when pushed to 50 liters per minute, performance dropped because the fluid moved too quickly, leaving an insufficient resistance time for effective heat exchange. Ultimately, our data proved that utilizing a counter-current flow at an optimized flow rate of 40 liters per minute provides the best thermal exchange performance. This study validated the performance advantage of counter-current flow in optimizing thermal exchange. That's all from us. Thank you.